Okay, we're going to go ahead and continue with our example 4.4. So we are on the second part of this. What is the acceleration vector at t equals 2 seconds? So we're going to go ahead and evaluate that. So we'll plug in our 2 seconds here into our t. So this would be 5I plus 2 times t, which is 2, j hat, minus 6t squared, which is going to be 2 squared, k hat. So we get 5I hat plus 4j hat minus 2 squared, which is 4, times 6 is 24, k hat. Okay, so this describes the direction of the acceleration vector. Okay, and this is in unit form. Now we can go ahead and find the magnitude of this though. That would be 5 squared plus 4 squared plus negative 24 squared, and all of that inside of a square root. Let me go ahead and put that into my calculator real quick. 5 squared plus 4 squared plus 24 squared, square rooted, and we get about 25. Okay, and this is going to be in meters per second squared. So this is our magnitude of acceleration at 2 seconds. Okay, so we're going to go ahead and do another example. Part of example 4.5, it says a particle has a position function r of t equals 10t minus t squared I hat plus 5t j hat plus 5t k hat in meters. What is the velocity and what is the acceleration? Okay, so we are just going to find those. So our velocity is again just our derivative with respect to t of our position vector. So it will be 10 minus 2t I hat plus 5j hat plus 5k hat, and this is now in meters per second. Okay, so that's going to be our velocity. Our acceleration is the second derivative of r of t, or dt, or dv dt. Okay, and so taking the derivative here, we have negative 2I hat, and that is it in meters per second squared. Okay, so this describes the motion. It's purely in the I hat direction. Okay, whoops. There is another part of this problem, part C, and you can read it in your textbook if you want to. It just kind of tells you how to describe the motion a little bit more, but I'm not going to worry too much about that at this moment. Okay, so I'm going to go ahead and talk about constant acceleration. And we have had this before. Okay, we've looked at this in one-dimensional motion, and it's going to be treated very similarly. Okay, so I'm going to go ahead and show you guys this through an example 4.6. Okay, there's a figure in your textbook 4.10, and it shows a skier moving down a slope. So I'm going to draw a representation over here. So this is going to be the y-axis, this is going to be the x-axis. Okay, and my angle is going to be exaggerated here. That's going to be 15 degrees. Okay, so this person is moving down this slope with an acceleration of 2.1 meters per second squared at a slope of 15 degrees. Okay, at t equals 0. Okay, so this is the acceleration vector here of this skier. This is the origin of the coordinate system, Her initial position and velocity are described here. Okay, so we're going to use these in order to find our x and y velocity components and position components, and that's what we're going to look for in part A. Okay, so the x and y components of the skier's position and velocity as functions of time. So first what we need to do is figure out her acceleration with respect to our x and y components. Okay, so the x and y components of the acceleration. Okay, so we'll need to do some trig again. Okay, so again, this is our acceleration, and this is our theta here. Okay, so we want to find a sub x and a sub y. Okay, so with some trig, our x component, that's going to be here, ax, and then ay will be in the y direction. Okay, this is going to be adjacent over hypotenuse, so this should be a cosine of theta, and our y is going to be opposite over hypotenuse, so a sine of theta. Okay, so we can plug those in. We have our A. Our A is just our magnitude of the acceleration, which was given as 2.1 meters per second squared. Okay, so we have 2.1 times cosine of our theta. Now it does say 15 degrees, but you can notice that this is actually below our positive x-axis. Okay, so this means it's in the negative y region. Okay, and when we're measuring angles, we go from the positive x-axis typically around this way in a counterclockwise motion, but we are measuring it opposite, so we're looking at clockwise motion. So we have to take that into account and place a negative there. Okay, so watch out for that. Okay, and here's the other one. I'm just doing them simultaneously. And once you plug these into your calculator, you get the acceleration in the x direction is 2.0 meters per second squared. And in the y direction, negative 0.54 meters per second squared. Okay. Okay, so what I haven't shown you in this lecture is how to kind of put these into our equations. So we want to know our position and velocity functions. So I'm going to go ahead and go to, where is it? Go to our textbook. And in this section here in 4.2, it talks about the constant acceleration. Okay. These equations will help you describe your motion. Okay, so what we need is going to be our x of t and our v sub x of t. So that's going to be equations 4.12 and 4.13. Whoops. Okay, so these two equations here. And then y of t here and v sub y of t. Okay, so our position and velocity in our y direction and our position and velocity in our x direction. Okay, so we'll use these in order to find those functions or equations. Okay, cancel. Okay, so let me go back here and I'll go ahead and try to squeeze some of it in here. So let's first do our v sub x. Okay. From our textbook, it states it will be equal to v naught x plus a sub x times t. Okay. So this is how we describe our motion. I should put up t here. Whoops. Okay. So v sub x sub not x. Okay, this is our initial velocity. That's going to be this component right here in front of the I. This indicates our x direction. Okay, so it's going to be 4.1 plus our a sub x, which we just found is 2 meters per second squared. I can just put 2.0 times t. Okay, so this is our velocity function, the x component. Okay, and we can do the same thing with our y. Whoops. Come on. Oh, shoot. Okay, hold on. Let me go to the next page. I'll go ahead and do it up here. Vy of t will be v naught y plus ay times t. Okay, so our v naught y is right here. The j indicates it's our y component. And so this will be negative 1.1 plus our a sub y, which we found as negative 0.54, and that's times t. Okay, so this is our y component of the velocity. Now we need to find our positions. So that's going to be x of t and y of t. So x of t, according to our textbook, is x naught plus v naught x times t plus 1/2 a sub x t squared. Okay, so we plug all of these values in. X naught is found here. That value is 75. It's going to be 75 plus v naught x, which again is 4.1, times t plus 1/2 times ax, and that was 2.0 t squared. Okay, so we can also say 75 plus 4.1 t plus t squared. Okay, this is x of t. That's our position equation in the x direction. Now we need to find y of t. It's going to be the exact same thing, but with y instead. So y naught is negative 50. So negative 50 minus, or it would be plus, but our v naught y up here is negative 1.1 times t plus 1/2 times a sub y, which we found is negative 0.54, and that's times t squared. Okay, so let's see, 0.5 times 0.54. Let's rewrite this as, actually I'll put it over here, negative 50 minus 1.1 t minus 0.27 t squared. Okay, so this is our position function in the y direction. Okay, so these are, or that was all part A. Now we want to go to part B. What are her position and velocity at t equals 10 seconds? Okay, so we want to plug in our time equals 10 seconds, and we will find those position and velocity vectors. So we'll go ahead and continue in the next video.